Wow. Wait, why?
Okay, we've got 1:30. Why don't we get started? Good afternoon, Research Methods. Oh, we can do better than that. Good afternoon, Research Methods. Good afternoon. All right. Welcome to week number 13. Hope you had a restful weekend. Hope that you didn't get into too much trouble with the wind last night. We had some scary winds, but could have been worse. I think we dodged a bullet, generally speaking. So good news there. So this is our last week before Thanksgiving break, and we have a section exam coming up. And I wanted to say before we get that far, congratulations to the many people in the room who scored perfectly on the last homework assignment. We had several people in the room who scored 25, another handful that did maybe 24 out of 25, and some folks who struggled a little bit with some of the items that we have in our 2x2. So we'll take a look at that before we get too far today to make sure everybody is comfortable with that. I did want to say a word about the exam. Not all that much is new. Same structure as always. Here we have out on the S drive. As well, out on Blackboard, we have this file, and it's really structurally the same as it's always been, the same kinds of ideas. We're testing mostly in this case for concepts. We'll test later on in the semester for our final computer quiz, but there won't be a lot of extended computation here. What I think is most important here is just to direct your energy toward when we begin with a new set of videos, a new set of PowerPoints, a new set of information since the last section exam. And that new material began on 10/28, where we did independent subjects and NOVA. So it's all listed there by date, and that's where you might begin to direct your energy for Friday's exam. Okay, but everything else here is the same number of points as always, same strategies for studying and so forth. Okay, I'll mention this again on the next 2 days that we meet, and we'll see if anybody has any questions. Then or now. Questions then or now. Okay, why don't we go ahead and see if we can get into maybe just a little bit of review on the 2x2. So at number 3 on our homework assignment, we had a simple 2x2, 2 levels of factor A, 2 levels of factor B, and you're asked to do all different kinds of permutations on factor A is significant, but B is not, and the interaction is, and lots of different pairwise comparisons on those. First, who remembers doing that? Okay, all right. Some people seem to really excel at that, and other folks had a little bit of difficulty on that. We did one toward the end of Friday's session, and so I'd like to do maybe 1 or 2 more. And just so that everybody is clear with this, if you'll join me out on Blackboard, we can go out to Blackboard together, and we can call up the file that's there on Blackboard. It's basically an answer key, but I wanted to make sure people understood how those 2x2s were constructed. Sometimes what happens is when you see it, it's fairly straightforward, but having to construct it is a little bit more difficult. It's kind of like when we're children and we're learning language, we sometimes understand a lot more than what we can produce. This is often the case, even in adulthood. Our receptive capacity is greater than our productive capacity. Okay? So we'll go to Research Methods. And we'll go to course documents. And I think toward the top of course documents, you have the file that we just looked at. It has all the details for exam 3. It says something like about exam 3, and I think I've got it as the one underneath here. Here's question 3 on homework 4. So I'll pop that one open. Hope you will too. Probably many of you have already done this, but you can click on any one of these and we get the various combinations that we had before. Okay. So I'll give you a moment to catch up. And when you have this file open, maybe you can raise your hand so I can see where everybody is. Okay? Okay, really good. Okay, so one particular permutation that we have is I've clicked on tab 3A. Factor A is significant, factor B is significant, and the A by B interaction is significant. Okay? So here you can see that we've got that pattern. A1 to A2, we're making that comparison, and we're basically saying that there has to be a difference on average between the A1 mean and the A2 mean. And hopefully you can see that there is a difference because we'd wind up with a higher A1 value than an A2 value. How many people are following that? Does that work for us? Okay, right? And then the same rule would apply if we look at the B factor. One level of factor B is in blue, the other is in this orange-reddish color. And when we take the average of the blue data points, that winds up to be higher than that for the red data points. Who's following that? Does that work for us? And hopefully it's really intuitive to everybody that we have an interaction because of the non-parallel lines. And what was our other method? Could somebody remind us? We can either use parallel lines or we can use something else. Subtraction, okay, right? So the idea would be if we differenced the blue and the red at A1, we'd come up with some non-zero difference. And if we difference the blue and the red at A2, we come up with exactly 0. Okay? So we wind up with different differences, and that constitutes evidence for an interaction. Who's okay with that? Does that work for us? Okay. And then we don't have to go through all the different possibilities, but here they are. You can see different patterns. This one's a little bit confusing because one's right on top of the next. It looks like we've plotted only one of them, but you can imagine that B1 might have generated exactly the same scores as B2, so there would be no effect of B2 because they're right on top of each other. They're obviously parallel, so there's no departure from parallelism. So here we have factor A as being significant, and that's all we've got, right, as for statistical significance. Nothing else is significant. Who's following that? Okay. Does that work for us? Okay. We go to, maybe we will step through each of these just so people can understand what's going on here. It looks like when we go from A1 to A2, we're not getting much of a change at level B2, but we're getting a huge change in level B1. Okay, so strong interaction there. Right? And A1 is going to have a much lower mean than A2 is, and B is going to be non-significant because the blues average out to what the reds average out to. Okay? Who's following that? Okay, really good. Okay. We go on to 3D, and here should be immediately apparent there's no interaction whatsoever. And we're getting the same mean at A1, that would be here-ish and here-ish. Okay, so A1 and A2 are not different from each other, but blue is clearly different from red. Stated another way, there's a main effect for factor B. Okay, and our last one, kind of an interesting one. It turns out that we have a very obvious interaction. That almost always jumps out at us first. We see what the interaction looks like. We get a higher level for the blue than we do for the red on average, and we're getting A1 equaling A2. Okay? Okay. All right, any questions on that? Okay, it's available to you out on Blackboard in case you want to practice. Sometimes it looks very simple when somebody else is explaining it to you, and then you've got this blank sheet in front of you, and you've got to generate those patterns. It takes a little bit of practice, a little bit of, quite a bit of critical thinking. It's actually one of my favorite exercises in this class because I think what it shows is that sometimes even relatively simple arithmetic, it's almost not even mathematics, right? It's just arithmetic, can require some substantial critical reasoning and quantitative reasoning. That's really what the Q stands for in these kinds of courses. It's quantitative reasoning. It's not just your ability to compute, but your ability to reason through, even with very, very small numbers. Okay, really good. So why don't we do this? Why don't we give you a moment to look over your notes. Why don't we have you go through slides 5 through 10, I think is where we are. Yeah, slides 5 through 10. And we'll see who's comfortable with that, and then we'll have you maybe walk me through. Many of you have watched the video. And while you're doing that, I'll just put up the video stats. Thank you very much. I did watch it a few times myself, but I noticed that there were 20 views. And so probably everybody got there one time, or at least nearly everybody got there one time, and a few others are mine. So we'll let you walk through slide number 5 through 10, with the question always being where are the significant F values, and then we'll see if you can step me through. Okay, look, I think I see some people appear to be finished. And why don't we just see if we can step on through. First, to get the conversation going, can we remind ourselves, ANOVA stands for what? Analysis of variance, okay? And so in the video we mentioned that we're going to be analyzing the variance shown here by way of this big multicolored pie, okay? And so one of the questions that we can ask is about F's, and then we're going to come back to similarly colored pies and ask about other features, not just the F statistic, but which effects, if any, would have a significant F value? If you think you know an answer to this, can you raise your hand? Which effects, if any, would have a significant F value? If you're not sure, can you raise your hand? So I can see who's struggling a little bit. Okay, a few people are struggling and a few people had their hand up. I think I saw Jenna and Mira raise their hands as you think you have some idea about where the significance might be, if we have any at all. Mira, can you help us out with what you've got?
There's none.
There are none, okay? What do you think about that, Jenna? Yes, we have no bananas. Yes, yes, we have no significant effects, okay? I would agree with that. I wonder if maybe Mira can begin to help us out in understanding her quantitative reasoning. We did some a moment ago. Here's some more quantitative reasoning.
Well, since there's it's denominator, and it's the biggest part,
Okay.
create a ratio less.
Okay, how many people are following that? How many people are not entirely sure they're following that? That was actually perfect reasoning. It's okay if we're not sure. Oh, that's okay. If we're not sure, I'd like to get it clear now. Is that okay? So that was actually the correct reasoning. Can we all yell out basically how the F ratio is formed? We had something up top and something on the bottom. What's up top for the F ratio? Between, right? And so it's basically between over. What's the one on the bottom? Within. Okay. And this might be something like a mean square. Can we yell out, what is our synonym for mean square? Variance. Okay, so this is an analysis of variance where we take a simple fraction, the variance between groups or conditions, over the variance within groups or conditions. And Mira has correctly pointed out that if you look at the way the pie is divided, we have within subjects, that's going to be our denominator term. It's taking up half the pie already. Okay? And as we've done, even in the opening slides today, I'm going to turn this on before I start losing people. Even in our opening slides today when we were looking at the A by B interactions and factor A and factor B, you can see that we've got a really good sized denominator. And if we look at the effect of factor A, it's quite a bit smaller. The blue is smaller than the red. So the blue component is going to be up top here. It's going to be outsized by the red component, and that's going to give us a ratio less than 1. Let's pause there and see how many people follow Mira's reasoning. And I think, Jenna, was that what you were going to say? Okay. All right. Does that work for us? So if we have now an F ratio that's less than 1, we're never going to make it out this way. Does that work? Okay. On the video, I point to this several times, and on 2 occasions I say the range goes from 0 to positive infinity, but on 1 occasion I said it goes from 0 to 1. Sorry about that. It goes from 0, I pointed to positive infinity one time and I said 1. But I think we all know it goes to positive infinity. 1 is nowhere near the critical value, and here factor A is coming up short. Similarly, factor B is going to be coming up short. Okay? Right? It's going to be coming up as less than 1, and factor A by B here in yellow is going to be coming up short as well. So we're going to wind up with no significant effects. As a matter of fact, the F ratio will never even reach 1, given this picture. Who's following that? Okay, so we don't know anything about the degrees of freedom here, right? We don't know anything about p-values, but we can use quantitative reasoning and figure out that from this alone, we're going to have some non-significant effects. Okay? All right, why don't we go on and now do a couple of variations. Maybe we don't need to do all of these, but just to make sure we're all on board, we'll let you take a look at this. And the question on the floor is the same. Right? Which effects, if any, would have a significant F value? And we'll let you take a look at that and think it through. And when you think you have an answer to at least some of these, maybe you can raise your hand. Okay, a few hands are up. I wonder if we can go with Katie. Can you help us out with what you think might be significant here?
Well, for this pie chart, the numerator is the biggest value instead of the denominator, so factor A will have a significant value.
Okay.
And so will factor B.
Okay.
They're both like very small, and then the numerator is large, so it'll be greater than 1.
Okay.
And then A times B will not be significant.
Okay.
Because that would have a value of 1, but I don't really understand
Okay, very good. All right, that was all really, really good. First thing we're going to do, we'll take factor A all by itself, factor B all by itself, and then the A by B interaction. In all cases, the routine is this. We put whichever factor of interest it is, in this moment it's factor B, shown here in blue, over the red. Okay, so we put blue over the red, and we have a really big area over a really small area, and that's going to give us some fraction that's quite a bit bigger than 1. Who's following that? Now, whether it's really statistically significant or not, we'll have to do some ANOVAs, and tonight you'll be reading in your guide what to click on in order to make the ANOVAs go. Some of you may have already tried that. I gave you a couple of clicks inside of the PowerPoint that you didn't have to do for today. But so we really only know if we ran it, but we have an overwhelming shot of being significant for factor A because the numerator is so much greater than the denominator. Our F ratio is going to be really big. And Katie was similarly correct with her factor B. If we look at the lime green area, it's quite a bit bigger than the red area. It's going to generate an F ratio substantially larger than 1. We'll pretend that's going to be significant. It probably would be. It would depend on the degrees of freedom. Katie indicated a little bit of hesitation on the yellow area, which is the A by B. You said that you weren't entirely sure why that was the case. Hopefully, to the best I could draw these, the red area and the yellow area are the same size. Does that work for us? Okay, and so however big the red area is, I'll call it 7. I made that number out of nowhere. We also have 7 on top. 7 over 7 gives us 1. Does that work? Okay, and
The value of 1 is not significant.
let's take a look at this. Okay, so we have to get out to the critical region, right? Okay, and so we start always at 0, and we need to get considerably past 1. Okay, we need to get out to some critical value here, and let's all yell it out. Our critical value comes from which Excel command? INV, right? Okay, whereas if we wanted the observed p-value, also called the sig, we wouldn't use INV, we would use dist, okay, right? And we would have 2 different ways of saying the same thing, okay? So from this picture alone, if we had some way of taking the total variability, maybe by indexing the sums of squares, one of the first computations we made this semester, and divvying it out into factor A, factor B, A by B, and what's within, we could figure out that probably these 2 are significant and that one is going to be non-significant. Who's okay with that? Okay, and Kip also had his hand up. Did you want to add anything to that, Kip? No, that's okay. And earlier on, when I said who thinks they have an answer to this, you're one of the early responders, but I think we're okay on this one now. Okay, let's go ahead and do maybe 1 or 2 more just to make sure it's all okay. And then if we're all on board, we don't need to walk through all of them. But I do want to make sure people are very comfortable with this. It becomes very intuitive. So this is nothing for you when you get to a section exam or you get to a quiz. You're really comfortable with this. Okay. All right, anybody want to help us out with what's going on here? Which effects, if any, would have a significant F value? Let's go with Jenna and then with Kip.
None of them would because it's similar to the previous slide. That would be a ratio of basically 1 to 1.
Yep.
So that's not significant to that.
Okay, Kip, anything to add to that, or is that the same? Okay, same answer and for the same reason, right? So we put blue over red, and hopefully that looks to you like these are perfectly quartered, so same size. We're going to wind up with a 1 every time. We need something bigger than 1 to make it out to the critical value. We'd never get there with this. Who's okay with that? Okay, does that work for us? Okay, let's see. Here's maybe one last one. I skipped over 1, okay, because I think the whole group is just about there. Anybody want to help us out with this one? Which effects, if any, would have a significant F value? Can we all yell it out? Maybe we all know. So 1 up here, which effects, if any, would have a significant F value? Okay, Megan, can you help us out? Factor B, you think would have a significant F value. So this green over that red would be significant. Okay, I'm leaning the other way. I'm thinking that the red is bigger than the green. Okay, right? Does that work for us? Okay, right. So I was thinking that actually B would be a relatively unambiguous case of probably being non-significant, even less than 1. Okay. Anybody else want to help us out? What do we think about factor A? Significant or non-significant? No? Okay, probably generates a ratio pretty close to 1. And same thing over here, a ratio pretty close to 1 for this yellow area, the A by B interaction. What I hope you'll take away from this, some people still struggle with this idea a little bit, is that each of these is completely independent of the others. You can have a significant factor A without anything else cooking as being significant. Factor B alone could be significant. The A by B interaction could be significant. And any 2 out of the 3 can be significant. And sometimes students get stuck on that. They think, well, if the interaction is significant, then something else must be. But it isn't necessarily that way. Can I ask you to, one more thing? This is something we haven't done in PowerPoint. Can you draw in the air what it would look like if we had a 2x2 and there was a non-significant effect for factor A, a non-significant effect for factor B, and a whopping big interaction? What would that look like? Can you draw it in the air? Only the interaction is significant and everything else is absolutely nothing in terms of significance. Okay? See some people making an absolutely appropriate move in the air. Okay, how would we, okay, I think I see it. Yeah, draw it in the air if you can. Draw it in the air. Maybe I'll help you out over here. So the only thing that's significant is the interaction. Here's A1. Here's A2. Okay, how would we draw it? Okay. There we go. I see several people doing it. How people are not sure? Okay. For the folks, can you hang on to that? Can you hang on to what you did? Yeah, okay, really good. Can we spin around and see what that looks like? All right. So Meg has it, and Jenna's got it, and Natalie's got it. Okay, maybe some other folks had it as well. It looks just like this. I'll do it maybe like that, and maybe like that. Okay, a simple crisscross. Okay, A1 has that mean, A2 has that mean, B1 has that mean, B2 has that mean. Okay, so not at all significant, but huge interaction because we've got the crisscross. People okay with that? What would that look like over here? Can somebody tell us what the colors might look like here? If you want to begin, we'll go with Kip this time. Yeah.
Pretty much everything small except for the interaction.
Yeah, right. I think that would do the trick. Right. That would. So we'd have maybe a really tiny red area that's equally tiny with factor B and factor A. Those all work out to maybe something like 1. And then we have this whopping big yellow area A by B as the interaction. Okay? And then if you were to plot that, it might look something like this. And out in SPSS, you'd have a really small sig value for the interaction, a really small sig value here, and very large sig values for A and B. Okay? All right. Really good. Okay, so hopefully now this is starting to all make sense to us. We have ways of partitioning the total variability in these examples. Factor A, factor B, and the A by B interaction. Okay, before we go on to the next concept, which is going to be Eta Squared, any questions about any of that? Any of the 2x2 graphing, any of the pie chart partitioning by color or by effect, or how it maps onto the F statistic and its distribution? Great, okay, why don't we go to this one? Okay, and why don't we give you a couple of moments just to look through your notes on this. I realize that sometimes people are very diligent. They make their notes, and then they go to 3 other classes, and your short-term memory has been overwritten by other important material from other classes. So we'll give you a moment to look over your PowerPoint lecture notes if you want. Why don't we have you look at slides 11 through 22. You can cursor on through if you want. These are all related to Eta Squared. That's the theme that links these slides 11 through 22, and we'll take some more questions and have you walk me through. Okay, hopefully some of that has come back to you from what you might have jotted down, and it's a little bit fresher. So now I wonder if somebody can start us out with this. Because you describe for us what Eta Squared tells us. Can somebody help us with that? What does Eta Squared tell us? That'll be our topic for the next few slides. Okay, thank you, Jenna.
It's a measure of effect size, like Cohen's d.
Yes, excellent. Okay, and we spent quite a bit of time, not a lot of time, but some time on Cohen's d. It was a measure of effect size. We had a slide probably 5 weeks ago, and it said something like "There's trouble in paradise." Who remembers that? There's trouble in paradise. Does anybody want to remind us what the trouble in paradise was? It did have to do something with Cohen's d, or we floated Cohen's d in there eventually. Yeah, thanks. Yeah, null hypothesis testing has some limitations. It has some benefits. It also has some limitations. And that is that I think we might have done something like this. We pretended that half of the group was in one research team, another half of the group was another research team, and you both went to the same conference, and one group had run a small n study, and the other group had run a large n study. And one group had concluded that yes, in fact, there's a significant relationship between our variables, and the other group said, nope, we came up non-significant. And it turned out that just having a larger sample size is sometimes sufficient to give us a significant effect. So getting statistical significance sometimes just depends on how big the sample was. Right? And we'll come back to that in a few moments when we work our way up to talking about power. But before we talk about power, we're talking about effect size, and Jenna is correct. Eta squared is a measure of effect size, just like Cohen's d is. One of the items that I mentioned only in passing, I wouldn't expect you to remember, is Kramer's v. And Kramer's v is also a measure of effect size, and we use that in the world of chi-square when we have categorical variables. We can use Cohen's d. If we have t-tests, there are a couple of different ways of talking about effect size. Okay, so it is about effect size. Can somebody now remind us in their own words, what do we mean when we say effect size? Well, what is that concept of effect size? We know it can be measured by Cohen's d. We know it can be measured by Eta squared. Kramer's v would give us an indication of effect size. Natalie's got something. Yeah, the strength of the relationship between variables. Sometimes we come up null, and one variable has no association with the other. One is not influencing the other. Sometimes the variables are very strongly correlated. Sometimes they're even causally related. And we can talk about the strength of that relationship by using a measure of effect size. And this is actually something very separate and apart from null hypothesis testing. Right? When we're talking about null hypothesis testing, we're rejecting a null hypothesis or retaining it without really saying that we have a large effect or a not so large effect. So it's a different kind of an idea. Okay? So here it is, Eta squared. Okay? And what we'll do is we'll see if we can go through and now not ask about the significant f values, we'll ask about which factor would likely have the largest Eta squared. So why don't we let you think about that, and when you think you have an answer, you can raise your hand. Okay? So it could be factor A, factor B, or A by B, or maybe we don't know. If we don't know, we can just keep your hand down. So which factor would likely have the largest Eta squared? Okay, we'll go with Natalie. Yeah, thanks, Natalie. Okay, the factor A would have the largest Eta squared. Yeah, that's exactly right. And do you have an intuition why that's the case?
The biggest one there, so like,
okay, right. Yeah,
so,
it's that simple, right?
yeah, because you mentioned that like sometimes when you have a big sample size,
When we have a big sample size, sometimes it's easier to find a significant f. Right, okay, right. But what we've got going on here is that Eta squared is going to be largest because the greatest area is occupied by the blue. And in just a moment, we'll take a look at what the Eta squared formula is, and that might make it very, very clear. So there might be, by chance, some covariation between large f values and large Eta squared values. It wouldn't have to be that way, but in this particular case, it might turn out that way. Okay? Jenna, is that what you were going to add? Okay, so factor A was going to be our largest Eta squared. This is the one with the largest effect size. Okay? So this is the strength of the relationship between variables. That's what Eta squared is measuring. And Natalie has reminded us of that. And just a reminder, different ways of assessing effect size. We're talking about Eta squared today. Previously, we've mentioned Cohen's d, and very briefly, we mentioned Kramer's v. Okay? So how many people have seen the Eta before? I had not seen Eta prior to taking a stats course or a research methods course. So that might be a new letter for us. 7th letter of the Greek alphabet. I think I've got that right. Anyway, there's the Eta. It's like a lowercase h. Okay? And what we're going to do is we're going to take the sum of squares for a effective interest, maybe the blue effect. That was the one for factor A. And we'll put that over itself plus the sum of squares for the within subject variability. Okay? Or in a within subject design, this would be the SS for the within condition variability. Okay? And we have that sum over the effect all by itself. So clearly, this number could never be any larger than 1, and it actually could be as small as 0. So Eta squared, if we want to understand its range, goes from 0 to 1. Okay? And sometimes when we're learning these new items like Cohen's d, or the f statistic, or the t statistic, it's helpful to know what are the possible ranges. Because at some point you might be doing some computation, and maybe you wind up with a negative sum of squares. And if that happens, you know that something is wrong. But if you wind up with a negative r value, that's not necessarily wrong. if you wind up with a negative r squared, you know something's gone wrong. Okay, so it's helpful to know what kind of range we're talking about. Eta squared is the same thing as r squared. It's one of the upcoming slides, and it goes between 0 and 1. Okay? All right, so here is another way of saying the same thing. SS effect over the SS effect plus the error term. Sum of the squares for the error term, which is also the within subject or within condition variability. Okay? All right, so now what we'll do is we'll see if we can use that formula. Hopefully you've got that down. It's a fairly simple formula, right? It's really just involving two numbers. Here's one, here's that same number again, and then there's our second number over there. And we'll create some more ratios just like we always do. And we'll start out with a 2 by 2, where we're interested in pretending that we are organizational psychologists. And we're trying to figure out in our Fortune 500 company, who's working how many hours, is there a gender effect, and might there be an effect by education as well. And there are different ways of thinking about how to operationalize an educational variable. Here we're going to talk about people who are relatively higher in their education and folks who have not yet gotten that far in their education. So people who have a master's or doctorate, we'll put them in one category. Folks who are not that far in their education, we'll put them in the other category. So that'll be 2 levels of that variable, 2 levels of gender, and we'll ask in this 2 by 2 if there are any differences in the number of hours worked. Who's following the design? Is that working for us? Okay. And these can be means all the way around, so we're comparing means in this 2 by 2 ANOVA. Okay. Here's what the SPSS output might look like. I'm going to say here, I'll ask you to break out of what you're in now. Can you use Excel? And we'll see if you can compute Eta squared based on what we have here. And in an actual test, I might not give you that number and that number. I'd ask you to figure it out. But just to walk you through, we're going to take the sums of squares associated with gender, and then the sums of squares associated with the error term. Those are these 2 numbers. We'll see if you can get your total and then your Eta squared. And when you've got that number, we'll let you call it out. And just so I can see where people are, if you do have it, can you raise your hand so I want to give everybody plenty of time, and I don't want you sitting there twiddling your thumbs if you've already got it. I'm going to take the picture away just for a moment so I can dial back to what the formula look like. Here's our formula, SS effect over SS effect plus SS error. And here are the relevant terms from this particular hypothetical Fortune 500 company. If you've got it, can you give me a signal by holding a hand up, or so I can see where people are? Okay, a few of us have it, some of us are still cooking. Okay, what if somebody can walk us through? Would somebody share with us what computation they did? Or better still, I wonder if you can yell out the answer if you've got an answer. Let them start out that way. What did we come to? 0.012. How many people have got that number? 0.012, okay. Somebody share with us just how they did that. It might be really obvious, but we'll make sure people understand. Who can walk us through? Thank you, Kip.
I did SS gender.
Okay.
SS gender plus SS error.
Okay, right. So you took this 343 and you divided it by the sum of these two, okay? And let's see, that's going to be something like 343 over something like 28,000 and some change. I can't do all of that in my head. And that worked out to 0.012, okay? And can somebody help us out with how we interpret the 0.012? What does that mean again? We mentioned it a moment ago. Let's see if we can get now a concept on that number. Right, so it's not just this weird number that floats around in the ether. It actually has some meaning. What is that? 0.012. We mentioned it's the Eta squared. What do we say that tells us? Yell it out. Eta squared tells us effect size, okay, right? And one of the ways of thinking about it is the proportion of variance explained, at least in particular analysis. And the numerator is the variability in the denominator. And what we're saying is 0.012, so something like, maybe 12% of the variance is being explained by this particular effect. It's a relatively smallish effect size, okay? But a lot of the variance has nothing to do, you can see that here. The total time, okay, it seems to be fairly small. Something like 10% of the variability there is going to be associated with the main effective factor B, which is gender, mass stock, or, the mass stock variable, which is the educational variable. Okay, one last one, and then we'll get to be really good at this. We'll let you put those together. This is 903 as our okay. And sometimes larger effect sizes turn out to be non-significant. It always depends on the degrees of freedom, but hopefully
Eta squared, you're not looking at that and saying, oh, those are all significant because they're less than 0.5.
that's right. Yep. The 0.5 would it recur? What's the probability of getting it by chance? Okay, and then over here. the probability of that occurring by chance. And then this tells us just how big a departure are we getting. Okay, so if we go back over to, is this the total?
Fish, if you go fishing and you don't catch a fish.
Another fishing net, same frame. I could get probably a big fish, a medium-sized fish, and some small fish, right? Or some really small fish. I probably could. The ability to find an effect if the effect is there. Is that what you had, Kip? And Nina, was that a hand also? Okay, thank you. Right. Okay.
You say that like 31% of the variance in your data is attributed to like your study. Can you just like explain why what you like by the design of your study?
Yeah, I think that's a very fair way of putting it. And more specifically, if you allow me to dial back, I apologize for. We're told we shouldn't go through these too quickly, but the idea would be if we had the big area here, and then